So good morning, everyone. Thank you for coming back. It's our second day of the mini school, and we are very happy to have Ionescu continuing his presentation on waterway problem.
Thank you. Thank you. Okay, so we're going to continue. We're going to continue what we started yesterday. So the goal for today's, for this lecture and for the lecture in the afternoon is to present three theorems that that make this case that in certain situations you are talking about small solutions, small in a certain sense, in a suitable sense, one can have long-term regularity of the solutions of the water wave. We are focusing on one very specific one, the main model, but there are others. So a specific model for waterways, which is written in this formulation, the Craig-Sulem formulation, and the formulation is we are talking about two functions, h and phi. H is the height of the interface. We are fixing Eulerian coordinates, and phi is the restriction of the potential to the interface. And they satisfy the system of equation dth and dt phi. There's a linear part here. Dth is minus phi plus a quadratic part. The linear part for the equation for h is dth is equal to absolute nabla of phi plus a non-linear part. So this is how one can look at it. One should think of these functions h and phi as small in a certain sense. So it makes sense to linearize around zero because the functions are small. And so we discussed yesterday we discussed energy estimates. There are two aspects to all of these processes. It's the process, they have basically two ingredients: energy estimates and some form of dispersion, some form of decay. And yesterday we discussed energy estimates. The strongest energy estimate that we discussed is so-called quintic energy estimate, quintic energy inequality, which I restated here just as to remember. So it's an energy inequality in terms of the so-called good variable. It turns out it's a technical point. One cannot really describe the whole problem in terms of the potential. One has to look at the good variable. But the content of this is that we have a control of the increment of the energy, and the control. So at the second time in which we want to control the energy is controlled by the energy at time t is equal to zero. So the first time t1 plus an increment, and the increment comes from the bulk integral. And the point of the theorem is that the increment is cubic. It's quintic, so in the sense that it has two copies of the energy and three copies of what would be the L infinity norm. So the L infinity norm of the solution. So that's so this is the quintic energy inequality, what we proved. It turns out that this is something very specific to gravity waterways. We actually discussed the quartic energy inequality. It's much more the cubic energy inequality. That's something that you should get for pretty much most equations. Like almost any equation, you can control the increment of energy. If it is to be well posed, then it has to go this way. The quartic energy inequality has to do with the absence of the quartic energy inequality is already more specialized to water waves, and to this specific gravity water waves has to do the absence of solutions. It's an algebraic fact about the absence of cubic resonances. So three wave interactions, which means that there are no solutions of this equation except for trivial solutions. Now for the quintic energy inequality, which is the one that we have there, there is more to it. It's not just it's something much more specialized. It only happens for a lot fewer equations, namely that even at the second level, the so-called four-wave interactions, in which we are looking at four frequencies that add up to zero, and for which the dispersion relations will add up to zero as well. Those are also of a very special kind, and those they don't come into the energy estimates because of symmetrization. So that's something much more specific for that only applies among the water wave problems, only applies to the gravity in 2D, which becomes 1D at the level of the interface. Yeah. Yes. The energy is modified. One can modify it The easiest way, the way we usually modify it, is through the integration by parts. We think that the extra term that comes in is basically, one would have to put it to the energy if you want. So when we integrate by parts, that's how it works out, both at the cubic level and both for the quartic energy inequality and for the quintic energy inequality. You can also try to guess it, but one gets it naturally just by integrating by parts. Okay, so these are the energy part. Now we are going to talk about a different topic today. I mean, we put them together, which is the issue of dispersion and decay. These are the slides that I had yesterday. And the first term, so we're going to have three theorems of this type. That basically what I want to say is that under various circumstances that it depends on what you want to do in the problem, what kind of information you have about the waves. We can construct solutions on long times. So this is the one we started with last time. And so this is the first theorem of this type. This is the first theorem of among the three theorems that we are talking about today. And they are saying the following thing. If we have control of the energy, and control of the energy means there's this certain dx to the power 1/2 that's applied to phi. It turns out that that's the algebra of the equation. When we diagonalize the operators, we have to apply this operator dx to the power 1/2 in order to get the diagonal variable. So if we have initial data that's it's small in the energy, so this is a medium kind of smallness. It's small in the energy means that implies some form of decay, because if we are talking about a big domain, so we are working on a big domain. We are working, either on the torus of radius r, but r could be ranging from 1 up to 1 to infinity. So this would be a big domain. So this is a medium type of smallness in which you assume that the energy is small, but it's not localized. So the energy could be distributed everywhere. And under this circumstance, you want to show that the time of existence which you can extend the solution is bounded from below. So so you can extend the solution for a time that's bounded from below by something that's of the form epsilon to the -6. If you think that r is large enough, so for the presentation, I'm going to think that r is large enough, because otherwise there's always another case to make. So r is bigger than epsilon to the -4. Turns out to be the threshold at which we have to change. So r is large enough. Then the time of existence that we get is epsilon to the power -6. So and I'm going to describe how we get there. So what's involved? There's an extra aspect to it, not just energy estimates. Energy estimates basically want to tell you that the solution didn't get worse. That we started with whatever we started at time t is equal to, and the best thing we can hope for is that the energy did not modify and did not somehow get much bigger in the time that we are looking at. Now, in order to prove something, we don't want to say just that the solution didn't get worse, but the solution did something that's good. The solution dispersed. So it's a different perspective that we take on the solution. We want to say something that the solution dispersed in a certain sense, in order to be able to get a longer time of existence. Okay, so this is the complete statement that if we are, let's say that r is bigger than r epsilon to -4, then we are constructing the solution on the time interval up to epsilon to the -6, so a long time interval that depends on the size of the initial data. And moreover, we control the solution up to that time, but by the twice times whatever we had control at time t is equal to 0. So a multiple of what we had control at time t is equal to 0. Okay, so that's the theorem that, in some sense, the simplest of the three theorems. So it requires the least because you have exactly control of the energy. So just a few words about it. Now, the case r is equal to 1, which is not the case I'm going to discuss. So at the other end, when r is finite, then this was already known. This is the theorem that I mentioned yesterday, the theorem of Berti, Frola, and Pusateri. Which leaves, so when r is equal to 1, the time of existence is epsilon to the -3. On the torus, so if it's a bounded torus, there's no room for dispersion. The best thing you can say is that the energy did not increase. There's no way to say that something decreased. Nothing can decrease on the torus, of course, on the bounded torus. Things only decrease because things separate in the space. Okay, so also this was also proved. So epsilon to the -3 time of existence is also proved by CGO on the entire real line. So she had an argument at around the same time that we had this paper. Now, the real improvement is in the case when R is large, in which case we get this long time of existence so we get this long time, and I'm going to describe what's involved in it, namely this simple form of dispersion. Now, I should say, the second theorem I'm going to do today, it turns out that if we make even stronger assumptions on the smallness, not only that the solution is small, but it's also decreasing at a polynomial rate, then we can actually prove a global result. So that's going to be the second theorem that we have today. So so this is the first theorem, but the second theorem I'm going to prove today is that under stronger smallness assumptions, we can actually get a global result. So that's also work with Fabio of about 10 years ago. Now, the point is, the reason why I wanted to discuss the theorem that this particular theorem is that localization, so meaning saying that the waves are localized in space, is not compatible with the wave turbulence, which is the ultimate goal. It's not possible to localize waves and at the same time make them random. So a wave turbulence has to do with the generic waves, and it's not possible to do both. It's not possible to both have them generic and localize them. So it's so this theorem, it's the global result depends on something else that's not relevant for the direction that we are working in now, namely the wave turbulence. Okay, so these are the remarks. Now, how do we prove it? I only have one slide of it, and I'm going to explain it a little bit at the board. How do we prove? As I said, what we want to show is not just that the energy. If we think of the energy estimates, the best you can say in the energy estimate, the energy starts with whatever it is, and that all the other times we don't lose information. What we want to show is that something happened with these waves when R is big that made them small. And for this, we use what we call, so we use a different way to measure waves. And so, I mean, I put the exact definition here, but let's just have a simplified definition, and then we'll see how we have to fix it. So it turns out, how do we measure decay? We measure decay using, we have to find a way to measure decay, and the best way to measure decay for this problem is using Strickard's estimates. So I would say that the solution, let's say U, and the correct Strickard's estimate is L4T, L infinity X, is also controlled by epsilon. So we want to bootstrap two pieces of information. We want to bootstrap the fact that the energy, so the high level energy is controlled by epsilon on the entire time interval. And then we want to say that the L4T, L infinity X norm of the solution is also controlled. And notice that this L4T, it's a different type of norm because it tells you that the solution cannot be big at all times. The fact that we have L4 in T, so it turns out that the key element here is the fact that we have L4 in time. So L4 in time tells you that if you're talking about a very long time interval, the solution, if it was to be the same as it started with the time t is equal to 0, then it would not have a control L4 norm, because it would be the L4 norm would be the length of the interval to the power 1/4. So as the length of the interval was getting big, that would increase. So we need to measure decay, and in this case, we measure decay using the Strickard's estimate. This is the simplest way, because I only have one slide. As you see, everything is on that slide. So the decay is measured in terms of the L4T norm. And let me run a simple calculation. Now, what does the L4 have to do? Why L4 and not L2 and not L6? It turns out that that's at the end of the day what's going to give the final result. It's the Strickard's estimate. So the Strickard's estimate is that if we look at the linear flow, and in this case, remember the linear flow was exactly this one, e to the minus it. So the dispersion relation is absolute value of nabla to the power 1/2 u, so f. And if we are to put a space here, and we are going to control this by the norm of f in L2, never mind it turns out that there's something to do with frequency projections. Let's pretend that the frequency projections work out to our advantage all the time, and they do. So if we are looking, it turns out that the space, if we know that the data at one time slice is in L2, the best space we can put here if we want to control L infinity is this space L4T L infinity X. And this is almost correct. It turns out it's not exactly correct. There's this issue that has to do with the frequencies that one has to track how exactly it turns out that there's also a loss of derivatives, but this is at the level at which the loss of derivatives doesn't matter. And also the time, so t, so so L4 in time is on a finite time interval, t has to be smaller than r. When r goes to infinity, then the time t is allowed to be large enough. But the point is that on bounded, if we were to be on bounded tori, then one can only have L4. One can only have L4 in time on a bounded interval. So t. So this would be on the interval 0t. It makes sense. If r is equal to 1, then of course there's no way for the wave to decay. The L infinity norm cannot be better than the L2 norm, so there's nothing that can nothing can improve in the weight when r is equal to 1. But this means that the L4 norm here can only be on an interval of size 1. So it's all consistent. The bigger the r, the bigger the size of the torus, the bigger time we can make, and this is the correct inequality. And it's written, so here it's written in terms of, there's a certain loss of derivative that's captured in the right-hand side there. Okay. Okay, so this is the strict adjustment, and as I explained, it's intended to capture decay, and the decay is captured in this L4 in time. If we were to have L infinity in time, then there would be no decay. We would only say that the solution does not get worse than what it started, but the fact we have L4 in time means that the solution will cannot be as bad at all times, cannot have the worst situation at all times. Okay, now let me explain how to use a strict adjustment. It turns out that we use what we call the Z-norm method. So the Z-norm, we need to measure the solution. I wrote exactly the precise norm that to use, but I'm going to have a simplified norm for the discussion just to show how it goes. It's a norm that captures decay. So it's a norm that it's the opposite, it's the counterpart of the energy norm, and we capture decay using this L4 TL infinity x. It turns out that we can only measure it. There's a certain technical point that's going to lead to the final result. It's only efficient to do this on certain time intervals. One cannot measure it on the entire time interval. One has to define the correct norm. It's very important. The choice of the Z norm is very important. Again, we are going to see this in the second theorem as well. The energy norms are usually, in some sense, cannot lose if you put more energies. But exactly what is the right norm that balances that? That's a critical choice. So the norm I wrote today, it's a simple norm in this case. Okay, so now let's see how would we prove. So let's assume that we have the strict adjustment. Is not hard to prove. It's a linear estimate. So for this kind of multiplier, one can usually prove anything that's true. That for this multiplier type of operators. So let me show how to put these things together, and also this way we're going to understand the role of the L4T. So so remember that the energy. So let's say the norm of U in Hn. So you just work with two basic norms, one at the level of Hn and one at the level of L infinity, with the understanding that at the L infinity can lose a few derivatives. So at the time t is controlled by U of 0 in Hn plus integral from 0 to t, and then we had U of s in Hn. So this was squared. Let's put them exactly how they are. So because it was at the level of the energy, and then we have this epsilon of s cubed. Yes. Epsilon of s is the L infinity norm. So epsilon of s is the L infinity norm. Which is what we had here. This was the quartic energy inequality. Now, if we pretend that this is epsilon, so we want to control this with epsilon, so we get that epsilon squared have to be smaller than epsilon squared. So one should think of this as a big constant. So the energy is allowed to grow by a big constant. And then we have this energy again, epsilon squared times integral from 0 to t, epsilon of s cubed. Yes, And then this is the L infinity norm. Now we don't have control of the L infinity norm in L3. We have control in L4. So this part will be smaller. So this part will be smaller than t to the power 1/4 times the integral times the L4 norm to the power 3. Times the norm of u in L4t L infinity x to the power 3. So if we use the so the L3 norm is controlled by the L4 norm, and then we have the L4 thirds norm, and so the length of the time interval is t to the 1/4. Okay, and now this would be equal to epsilon as well. So if we plan on a bootstrap, this would come as epsilon as well. So what we need in order to close the bootstrap, we need that this contribution here is smaller than 1, much smaller than 1. So what if we count them, we have epsilon cubed t to the 1/4 have to be smaller than 1 in order to be able to close, which would lead to t is epsilon to the -1/12. It's epsilon to the -12. Okay, this is a little bit of an idealized argument, because it turns out that one also has to control back. One has to put back one has to control the z norm again. When we control the z norm, we cannot close on such a long time interval, and we have to lose half of it. There's a certain balance that we have to do. I didn't explain. The argument's a little longer. I didn't explain why is that this time the L4 control is only on a bounded interval. It has to do with the fact that you have to control the z norm through we have to put it back into the equation and control the z norm. And when we do that, we can only run this argument on half of this time, because we have to lose on the other side something. And at the end of the day, it becomes epsilon to the -6. And so that's how and this is how the argument goes. So that's now you can see we can compare the numbers. So if we were to use just an L infinity norm here, if we were to use an L infinity norm, that instead of getting t to the 1/4, we'd have to integrate. We have to lose the entire time interval. So instead of getting t to the 1/4, we're getting t to the power 1. And t to the power 1 would lead to a time of existence epsilon to the -3, which is the same as if the size of the torus was equal to 1, in which case we don't have any dispersion. So it's this L4 here that leads to the better power of t to the power 1/4, because we control the L4 norm with the L3 norm, and this extra power. So this is the power that we lose in the L3 norm, and then so it's ultimately the numbers. This ultimately comes from what choice do we need to make in the Strickard's estimate. It turns out that in one dimension, the best choice that we can make is L4 in time. In higher dimensions, one can make the choice with L2 in time. So in higher dimensions, the analogous Strickard's estimate comes with L2 in time and L infinity at the expense of losses that can be accounted for. Now, if you were to have an L2 in time, and even if you were to have an L3 in time, there would have been no more loss here, and that could have led to a longer time of existence. So the Strickard's estimate, at the end of the day, the result. So basically, what I mean to say, this calculates a little bit of so it's a little fast, and of course, it doesn't capture all the real issues. But what I mean to say is that for the Strickard's estimate, what I mean to say is that it has to do it's a way to measure time decay, because this LP in time, this finite LP in time, measures time decay, and it can be put back in terms of the equation. Okay, so that's the Okay, so this is this theorem that it's a simple theorem that gives us a long time of existence for the problem which we have in which we have bounded energy. Okay, now I'm going to discuss. So this is the first theorem. I'm going to discuss now some work that we've done, that Fabio and I have done a few years ago. That's part of this story, in which, in a very specific situation, it's a stronger form of smallness that we need to assume. In a very specific situation, we can prove a global regularity result. So this is the third theorem. Third, if we account for the fact that we also had the quintic energy inequality as the first theorem. And it says the following thing. It's a different form of smallness. I'm going to write it. I'm going to read it. So this is a theorem that we actually proved a few years ago, about 10 years ago. It was after a result of C.J. Wu, who proved a similar theorem, but with the bounded time of existence, but the bound being much larger, like it was exponential in the time in the smallness of the form e to the minus 1 over epsilon, where so it's an exponential time in terms of the smallness of the initial data. So the third theorem says the following: if you are looking at initial data that's small in the energy, so the first part is small in the energy, u naught, so to u, in this problem, u is basically h plus dx to the power 1/2 phi. So this is what the so-called Hamiltonian variable that's consistent. That's the right one to measure in L2 in order to capture the right number of the rate. So we assume that the initial data at time 0. So you have control of the energy, the same Hn over here, and they have control of one more kind of energy, and that's something that is going to capture decay. So the object that we have is x dx. X dx is a vector field. And it turns out that the important thing about this vector field is commutes the right way with the linear flow. So it's another form of energy, which, if you see what it does, it actually tells you that, never mind the dx, if you were to think that x times u naught is in L2, that would mean that not only the energy is small, but the function is to be localized around x is equal to 0. It identifies the point x is equal to 0 as different from the others, and the energy is measured relative to the distance from that point. That's because of the factor of x in front of the vector field. And so that's the correct way to look at it is x dx, because this is the vector field. And then we have, again, a z-norm. So the z-norm is not exactly comparable. So the z-norm is small. So this is going to be done. The principle is the same as the one that we had in the earlier theorem. We want to control energies. The energies will tell us that some high order derivatives they don't deteriorate, and then to prove decay, we need to use separate kind of control, and this is described through this z-norm. Now the z-norm in this case, I wrote it here. It's actually still pretty simple. So here I have the formula for u naught, the one that I wrote on the board. So the z-norm is a norm that we write in the Fourier space. So you look at the function, we take its Fourier transform, and then it turns out there's a very good way to do that. We put the L infinity norm, but in the Fourier space. So you don't measure the L infinity norm of the function. We wouldn't be able to propagate it. At time t is equal to 0, we could measure it, but we wouldn't be able to propagate it. What we do is we measure the L infinity norm in the Fourier space. That's why the norm is not comparable. If you want to think of what these other norms give, they give some kind of L infinity norm, L2 norm in the Fourier space. You have an L infinity norm in the Fourier space.
Why in the previous result, the energy estimate was given for H and the good unknown, whereas
yes,
given for H and phi.
No, it really should have been the good unknown. It should have been instead of phi. So at time t is equal to 0, it doesn't matter which one you put. I think we can probably pass. So I think this is still correct as written here, but the energy itself, in the proof itself, you should think that in the proof you do the proof for the good unknown. I think this is correct here as well, in the sense that we can afterwards pass, because I gave up a couple of derivatives. This in hn, and then I had hn plus 2, so it's probably correct too. It's probably correct written as well. Yeah, I think that's probably what it meant, that here we assumed a few more derivatives in the initial data in order not to have to pass to the good unknown. But in the process of proving energy estimates, you actually have to pass the good unknown, otherwise they don't close.
In the other slide, you also have the definition of the time, you have the time involved.
Yes. Yes, this is going to be, so, I'm going to talk about that. So the Z norm, we define it every time. It's gonna be defined at every time. So the Z norm. So this is it's a little more complicated. There's a time involved here if you want. So this is the decay is t to the minus 1/2. So the solution decays like t to the minus 1/2 when measured in L infinity. So there's a time there, but because we have more, in some sense we know more about this. So it's not in our best interest to measure it just in terms of L4 in time. We measure it stronger. So we say that we have control of decay like t to the 1/2. If you think here we claim control that the solution in L infinity decays like t to the minus 1/2. That's a lot more than saying that it's in L4 in time. If you want to think this norm is stronger than the L4 in time L infinity index, because t to the minus 1/2, of course, is going to decay. We have room relative to L4 in time. And that comes from the fact that the initial data is localized. The reason why I can prove something this strong is because the initial data is localized. Okay, so then basically the claim. So the claim. So I'm going to read now the theorem. I explained pretty much everything that's in the theorem. So we are starting with initial data that is in this agent space, and also the vector field. So this vector field S, which at time t is equal to 0 is x dx. Afterwards, the vector field is actually x dx plus t dt. And it turns out the correct power is x dx plus 1/2 t dt, the 1/2 coming from the fact that it's absolute value of dx to the power 1/2. So then what we say is that we control the agent norm of the solution, using the vector field, and the L infinity norm of the solution with this polynomial decay in time t to the power minus 1/2. And this turns out to be sharp. Now we don't control them so well. So the energies, on all the energies we lose factors of t to the delta. So we on one hand, at time t is equal to 0, of course it doesn't matter, it's t to the delta, but as the time increases, we are not able to control the energy without any loss, but we lose small powers of the time for a small value of delta. But this is compensated by the fact that we gain control of the L infinity norm with a much faster t to the minus 1/2. So we lose small powers of delta, and we gain at the level of L infinity, we gain t to the power minus 1/2. So this is the conclusion. Now it turns out that this is a quick way to state the theorem, but it turns out that the content is actually on this slide. The linear solution, if you think at the linearized level, the equation is dt minus I lambda u, where lambda is the dispersion relation that's equal to 0. So at the linear level, you think that the solution is of the form e to the it lambda times the initial data. It turns out that that's not correct globally in time. In order to be able to get a global in time theorem, we need to correct the oscillation, and we correct it by this factor e to the I g c of t, and only after we correct by this factor. This factor depends on the frequency and depends on the time. There's actually a written formula there. Depends on the frequency, depends on the time, and only after we correct by this factor, we can say that the solution converges as the time goes to infinity. And this is what's called modified scattering. If it wasn't for this factor g, that would be the standard scattering that we get for most equations. It turns out the standard scattering to get for most equations is not correct for the gravity waterways, and this was the main improvement that Fabio and I did over the work of CJU, for example. And one needs to have this particular correction. If we want to measure it roughly, my plan was to get through this term, but we'll see. If we don't, then I'll come back to it. If we want to measure roughly what's the effect if we look at this formula and we want to understand the, roughly what are the sizes, well, the oscillatory factor that we have here is e to the it times lambda of xi. Lambda of xi is absolute value of xi to the 1/2. So it's basically of the form e to the it. So it grows polynomially in time. Now, if we think of what's the correction, the size of the correction, well, so the size of the correction, the correction cannot be prescribed. You don't know what the correction. The correction is, you only see it as you advance in time. So at time t, we have to integrate the entire solution from time t is equal to 0 to time t to get the exact form of the correction. So it's not, there's no way to prescribe just by looking at the initial data. But in a best case scenario, the frequency does not deteriorate. So this would be, let's say, u hat of xi0, and then we integrate the 1 over s plus 1, and then we integrate the 1 over s plus 1. We get a log of t. So one could think that this correction g of ct, if we are to write like a simple form of how it looks, g of ct would be something that depends of xi. So let's say xi, a constant that depends on xi times coming from the integral log of t. So the integral of 1 over s plus 1. So this has, it's a correction that as the time goes to infinity changes logarithmically in time. It's smaller than, of course, the free term, but it's still there. So if we want to have convergence, and if we want to do the whole to prove the whole theorem, then we need to account for this correction. And it turns out that even if you don't want, so it turns out that we are kind of forced. So you could wonder, okay, let's say I don't want to deal with that part. Can we just prove global regularity without dealing with that part? It turns out it's not possible. So that was basically what Fabio and I noticed, that in order to prove global regularity, you actually need to identify this correction as part of the bootstrap in order to be able to prove global regularity. So one cannot just prove this part of the theorem that has nothing to do with the specific correction without understanding the correction as well. So that's so this is the theorem that Fabio and I proved. I wanted to give a few ideas on how to prove it. Notice that this correction, if we were to think of the time that's exponential, so let's say that we are looking on a time that's of the form the time that's of the form e to the 1 over epsilon, then the correction doesn't play a role up to the time because the correction picks up a factor of log of t. So that would be a factor of 1 over epsilon, but it also picks up two copies of the data, so that would pick up an epsilon squared. So it doesn't play a role up to exponential times, but it plays a role globally in time. So that's my point. Okay, so now we're going to talk about the proof of this theorem. And also this theorem says this is only true. This is the only result that's global. It's only true on the Euclidean space itself. It's not possible. There's no, if you're on a big torus, so it corresponds to I is equal to infinity. If you're on a big torus, there's not enough dispersion. One can go to some kind of time that depends on the radius, but one has to do different. There are different arguments that go through. It's a different mechanism that doesn't go through dispersion. It's a different mechanism. You know, to construct global solutions on finite domains, one cannot do it this way. One has to go through periodic solutions or quasi-periodic solutions. So it's a different mechanism. Okay. Okay, so I'm going to describe now the ideas quickly. I don't know if I'm going to finish them, but if not, we are going to come back in the afternoon. We have three things here to control. We have to control two energies, and we're allowing them to grow, and we have to control one L infinity norm. I'm going to erase the number of derivatives. It turns out that one has to put the correct numbers here, but that's not the hard part. So I'm going to pretend that we have to control energies and L infinity norm. Now, the energies, there are two types of energy. You have the energy that has to do with the vector field and an energy that has to do with the usual derivatives. And we can put them together. So if we think that the vector fields that we apply are either all of these pointwise derivatives, or we apply one vector field and a bunch of pointwise derivatives. So these are the energies. So it's kind of like a generalized type of energy. If you think, when we do energy estimates, we apply d by dx or d by dx twice or d by dx 3 times, and that's what would be the most basic energy. In our case, we do that, but we also are allowed to apply the vector field S exactly once. The vector field S can only be applied once. All the other energies can be applied many times, all the other vector fields, but the one that grows in X can only be applied once. Okay, so then we have to so here I sketch the bootstrap, the so-called bootstrap estimate. What we do is we control two things. We control these energies in L2, and we control them with the growth. With the growth in time, there's that epsilon times to the power t to the power delta of the number of vectors. In this problem, it turns out that the delta can be taken the same delta. In other problems, you might need to the number of vector fields, the growth of each energy at a time, that could change. But in this problem, it's a little easier to pretend that there's only one delta that we need to use. So we control two things. So we control the energy with the growth, and we control the Z norm. So let me remind what the Z norm is basically the L infinite norm. If we erase these factors, which are kind of technical, this is basically the L infinity norm in the Fourier space. So we control this with a bigger constant epsilon 1, and the initial data we control it with a better constant epsilon naught. Then the conclusion is that we control everything with a better constant. So that's how the bootstrap goes. So we control the energy. So we improve the bootstrap estimate in the sense that here we have the better constant, and we improve the bootstrap estimate on the Z norm in the sense that we have here the better constant. Okay, and the Z norm is this L infinity norm, and I'm going to describe what's involved in the argument, kind of like at a very vague level, just to kind of like what I did earlier. It turns out that in this problem, we could have used the quintic energy inequality as well. Of course, at the time we hadn't done it, but it makes no difference to use the quartic energy inequality. And the reason why we don't benefit from the quintic energy inequality is the quintic energy inequality does not apply to the energy of the vector field. There's more symmetrization when we do the quintic energy inequality that requires more than just the fact that there are no resonances, and it does not apply if we were to apply the vector field. The vector field changes a little bit the symmetries of the equation. So we don't have access to the quintic energy inequality in the context of this problem. So we can only work with the quartic energy inequality, which I wrote it there. So these are the two quartic energy inequalities for the solution and for the solution with the vector field S. And the first one, we could have used the quintic, but of course, since you don't use the second one, since we don't have the second one, it will be no difference. And then notice we can close back. So these energies, this is the formula after I subtracted the energy on the right side. I just put everything in the right hand side. So notice what we have is here we have control of the energy, and here we have control of the L infinity. We have to put L infinity norm squared, and squared comes from the quartic energy inequality. Now, if we look back at what we know in the bootstrap, if we have control. We have control of the energy with the slow growth, and what we need in order to close this part, we need that here we have this L infinity norm has to decay like 1 over t. Because what we have, if we have here like 1 over t, and this would be like t to the delta, then we have t to the delta, t to the 2 delta, t to the 2 delta minus 1. We integrate and we get exactly, so we get exactly what we need. So in order to close the energy argument, we need to have what I wrote here, the decay. It's the pointwise decay. Is the strong analog of what we had as the pointwise decay to the Strickland's norm, because, of course, this decay is much faster than the L4 norm. Okay, so then this means that we need to control this energy. And it turns out that, so there I just rewrote the Z norm. And it turns out that so it turns out that the L infinity, we still have, we don't have exact the Strickland's estimate. We have the corresponding dispersive estimate that corresponds to the Strickland's estimate, which in this case is e to the minus it dx to the 1/2 f in L infinity is controlled again up to ignoring derivatives by the norm of f in the Z. So the Z norm is arranged times t to the minus 1/2. The Z norm is arranged, it's arranged in such a way, it's strong enough, in such a way as to get this control with the gain of t to the 1/2. And so that's what's required. The t to the minus 1/2 had to do with what we need in order to close the energy estimate. And it turns out that for that particular Z norm, one needs to put the L infinity norm here in the Fourier transform in the L infinity norm, and then one gets the t to the minus 1/2. If we only had control of L2 base norms, then one can only get things of the form that we had here, which was with L4 in time. If you think L4 in time, it's more like at the level of t to the minus 1/4, which is not quite enough. Okay, so that's the logic of these norms. Okay, so these are the slides that. So this is the logic of the norm. If we have control of that Z norm, then this is a linear estimate, so it's again a simple estimate to prove, and then we could control the decay. Now, what's the remaining couple of slides is how to improve, how to do the bootstrap for the Z norm itself, because that's a little bit harder. I didn't describe this for the strict transform, but I'm going to describe this here because that's how we see that's how we see the modified scattering. That's how we see that function g that we had to put in. Okay, so now how do we do that? So I'm going to rewrite the equation. I write it in this kind of format that I used last time as well. It's kind of like a simplified format, in which we are looking at so this is this DTU. We put in the faces, so we look at the profile. We have certain symbols that we are gonna. They have explicit formulas that verify various suitable. They verify various suitable identities, and then here we have this would be something of the form U squared, which in the Fourier space becomes U hat of xi minus eta times U hat of eta. Everything at this level is done in the Fourier space. The xenon, the control of the xenon is done in the Fourier space. Okay, and we have various combinations because we get either U could be either the solution or the complex conjugate comes out the same way. So you have U plus and U minus. And the corresponding faces, they come with plus and minus as well, because they are they're either the solution or the complex conjugate. And then we write the Duhamel formula. I wrote the Duhamel formula here because we are going to use the Duhamel formula in the last discussion as well, so in the last theorem. And the Duhamel formula, so you have U hat of ct, this U hat of c0, plus we get this integral from 0 to t of these Duhamel contributions. So these are all written here. We just integrated. Here we have all the possible combinations, and the only part that's not precise here are the symbols, but you should think of the symbols are going to cooperate with us. In many ways, they are going to cooperate. Now, as we've seen, these faces, they do not vanish. This was part of the reason why we had the quartic energy inequality to begin with. And because the faces do not vanish, we can integrate them. We can do this. We can take this integration here and do the normal forms at the level of the Duhamel formula, and then once we, I'm putting the faces, so the faces that don't vanish, they become denominators when we do the integration by parts. They become denominators, but because they don't vanish, I can still put them with the multipliers and hope that they are not going to mess things up too much. And that's what we do. And then what we have is, so we have a cubic term. So originally had quadratic terms here. When we integrate by parts, d by dt, so integrate by parts, so you get cubic terms in the Duhamel formula. And then, so this is the formula that we get. And I'm going to ignore the aquatic terms that becomes pretty messy to estimate them, but I'm going to ignore them for now. Okay, so now the faces that we get, they are now combinations. Now we have one more frequency, so they are lambda of xi plus minus the other contributions of lambda. And it turns out, if we just look at this integral, it turns out that it's pretty good everywhere. So what we'd like to say is that this decay is like better than 1 over t, because this is d by dt. So if it decays better than 1 over t, then we can integrate it. And it turns out that at most places it decays better than 1 over t, except at the resonances. And we have the so-called space-time resonance, the cubic space-time resonances, and there the decay is exactly 1 over t and cannot be integrated. So if we put them exactly, and I think I have them on the next slide. Okay, so when we put them, the space-time resonance, the resonance of the problem, there is frequency. Given a frequency c, there are 3 other frequencies that come in, and they're only of this type. They're only the so-called what I called before the trivial resonances, in which it's a very special type of the trivial resonance, in which the other frequencies that come in to this equation are c minus c and permutations of that. It turns out they can come in any position. And now what do we do? So we look at this contribution. We have to integrate on suitable scales around these frequencies. And when we look at the contribution of these terms around the frequencies, then we get this factor, the contribution so we have to integrate from 0 to t, and we get this integral. And it turns out that in order to so here we have dt u prime is equal to some expression, and we need to conjugate. We need to conjugate by that in order to eliminate it. And when we do that, so you need to conjugate by this phase. So you conjugate by the phase c to the I L C T, and the phase is determined. So there's an exact formula there, but it's determined in such a way as to cancel the contribution of this special resonance is the one that corresponds to the frequency c and the frequency minus c. And once we cancel them, so we cancel these contributions. Afterwards, we get. So we cancel this. There's only one term. Thankfully, there's only this contribution that doesn't decay at the right speed. And once we cancel that, we get d by dt of the function having better than 1 over t decay. So after this conjugation, the z norm itself, we can control it by in a decreasing way. And that's this is how we prove the global control of the z norm, and then having global control of the z norm and having this L infinity dispersive estimate that gives us afterwards the global control of the energy as well, and that's how we close the full bootstrap. Okay, so this is the third theorem. So it's if we were to put in some perspective. So here I described the two. It's basically the logic is that we need to understand the solution in 2 ways. We need to understand the level of energies, which in this case we actually allow them to increase slowly, and we also have to allow all the vector fields to put them in the energy, because in some sense d by dx is not very different from any other vector field that commutes to the linear part of the equation. So I have to allow for those. And then so there's one aspect of the problem, and in order to close, we need to have a second way to understand the solution, in which we want to understand there is decay. There's something that improves as the time increases, and that we do using this pointwise decay. In this case, in the pointwise decay. In the other case, we had some kind of strict cuts estimate that was measuring this decay, and this leads to these are the best results so far about the gravity waterways. These are the global and the long-term result for this problem. Now, what we are going to do in the last class, in the last lecture, we are going to discuss the wave turbulence. This idea. So one can think one can stop here. One can stop at the level of understanding the long-term regularity. But what we like to do is to understand how can one use this what we know about global regularity to pass to the so-called wave turbulence to understand the wave turbulence of waterways. It's a very classical problem. It's a wide open problem. There are really no good results, and our theorem is not particularly good either. It's Since it's the first theorem we could prove on this, but one would like to do a lot more, and one has done a lot more for other problems. It's a classical problem that goes back to, it's the center of this so-called Hasselmann model of climate variability, the center part of it. Now what I'm going to discuss, so I'm going to discuss this a little bit more, but just as a quick preview. There's a lot of, so first, Hasselmann got the Nobel Prize for this. So many of the results are attributed to him. But in fact, from a mathematical point of view, Zakharov has done just as important work. So the equation that's the relevant equations here, the wave kinetic equations, they're actually sometimes called the Zakharov equation. And it turns out that the point of view, at the simplest level, one can take the point of view that understanding the wave turbulence is equivalent to understanding long-term regularity of the solution under the assumptions that the initial data is generic. So the core assumption there that we didn't have before is that the initial data should be generic. For all initial data, there is no such thing. There's no wave kinetic equation. But for generic initial data, we have to prove that we can do better than for general initial data. And that's going to be, so this is the last part. There's one more aspect, namely the fact that the data has to be generic. And for that type of initial data, you can control the solutions. And so that's what we're going to discuss in the afternoon. Thank you.